Dude, let me see now. Now, today we're going to talk about two new coordinate systems. And in my head, when I said new, I had quotation marks around it because we actually already talked about cylindrical coordinate systems. I don't know if you guys remember.
Yeah.
Because when we did polar in as my inputs, if I just add a z component, that's cylindrical. Because a cylinder, a basic cylinder is a circle repeated. So isn't that just a circle, like polar coordinates in the xy plane now becomes the r theta plane. And then if I just add a z component, that's a cylinder, and that's why it's called cylindrical coordinate system. Because it can handle cylinders very easily. So the cylindrical coordinate system is pretty straightforward. If you look in section 13.5, page... Hello? Page 918. So you got your theta, you got your r, and now you got your z. That's how you describe a point. So obviously, if you ask somebody to turn, to walk out a certain distance, and they go up or down, you can hit any point in 3 dimensions, right? So that's a valid 3-dimensional coordinate system. The conversions in cylindrical are easy because we should already know polar conversions. And the last conversion is z equals z. That's awesome. So to go from x, y, z to cylindrical, or from cylindrical to x, y, z, it's just the same as our polar coordinates. So for example, x equals r cosine theta, y equals r sine theta, and z equals z. That's nice. And how do you go back? What do you know about r in terms of x and y? R squared equals x squared plus y squared. Theta equals, who remembers this?
R
Inverse tangent x, y over x.
Y over x, cool. And z equals z. Gotta like that. So this is an example of a, you can do a lot in 2D. You can have some different 2-dimensional coordinate systems, and if you just add a z component, that's a very simple way to make it now a 3-dimensional coordinate system. Identify a point in 2 dimensions, and then just lift it up or push it down. That's your z component. Almost feels like cheating, right? So nothing major there. We have to kind of talk about what would integrals look like, obviously, in cylindrical coordinates. And in polar by itself, remember, let me not do that. In polar coordinates, we had that little polar rectangle that we talked about. And it ended up, we eventually got to the point where it was r, d theta. So incredibly enough, now to get that last component, the last coordinate, you just throw in there what? To make a volume out of it. So this is sitting in the xy plane, r theta plane, multiplied by dz, the change in z. And actually, you normally put that right there. Pop. So now it goes from, there's the area in the r theta plane, multiplied by dz to get out of the plane. Now you've got the volume. Okay, how are we doing so far? So cylindrical is not a very big deal. Let's try an example problem. If I brought I am noteless. Oh, here. Oh, perfect. Example 4. 923. Actually, let me see if I can do this. Just in case your booklets, let me see if I can throw this up here. There we go. So there's example 4. It says find the volume of the solid between the cone z equals square root of x squared plus y squared and the inverted paraboloid z equals blah blah blah. Okay. So here's the cone. Z equals square root of x squared plus y squared. So of course as x and y grow, z gets taller. That's why you end up with the cone as you go out. So higher height. And the paraboloid max is 12, goes down from there. So just look at the picture. How do you think I'm going to find the polar coordinates, the region in my polar plane down here that I'm integrating over? How am I going to find this?
Convert from x, y to polar.
All right, that's a good first step. In general, what I do is I take these and do what?
Make them polar.
So they equal to each other. If I don't change to polar first, they so suck to try to solve radical x squared plus y squared equals this square. Let's screw that.
Yes, r squared equals.
I like it. So what's it say? Z from z equals
R.
So z equal 12 minus r squared. I love it. So do this real quick. Set those equal to each other and see what you get. We're trying to figure out what that region we're integrating over looks like. It's the shadow of where they meet. See that? Where they meet tells me what this region is that I'm using to integrate over. X squared plus y squared is r squared, and it's minus. Yeah, minus x squared plus y squared. Cool. So you end up basically with r squared plus r minus 12. Right? And of course that's beautiful. How do you factor that? So I get r equals 3 and r equals negative 4. What do you think those relate to? What do you think that this one relates to? Which one of those answers relates to this? 3. What do you think the negative 4 talks about? What do you think that's all about? Because does this paraboloid stop there?
No.
No, keep going. So in the cone, when I write it like this, I lose information about is it above or below or both. I lose information, does it look like that or does it look like this? Right? I don't know if there's another like negative cone underneath. Mathematically, I don't know. We know there isn't. But if I extended this paraboloid down and looked at the negative cone, they would meet where r equals 4, basically.
From 0 to 3.
So we just want the 3 one. You can always double check. I mean, if you make z 3, right? Because z equals r, so if you make z 3, don't you get x squared plus y squared equals 9? Don't you get that side also says r equals 3? So that's where they meet up here. Everyone's fine. Okay? Alright, semi-decent. So now I know what about my polar part? What about my just two-dimensional thing? What happens down here about r and theta? R goes from what to what? Theta goes from what to what?
0 to 3.
So R goes from 0 to 3.
And theta goes
0 to
from
2 pi.
0 to 2 pi. Got to go all the way around to capture this whole thing, right? Okay, cool. Of course, those set up what for me?
Your
limit.
Limits, beautiful, right? So you see how to start attacking this. You almost always want to draw a 2D graph for yourself. Just dealing with the region of integration. So you can see what your limits are for that. Cylindrical kicks ass, because once you get that, you're basically done. Z is easy. Z goes from, like we already said, R to 12 minus R.
So what is equals to?
So how will this interval look?
We don't want that, we want Z. Because oh, I see, because it would be going back out.
So the inner one would be what?
R to 12 minus R.
I love it. The inner one deals with Z. So Z goes from R to 12 minus R squared. What does R do?
0 to 3.
0 to 3, and theta spins me around,
0 to 2 pi.
so I pick up the whole thing. Cool.
What are we integrating now? It just, is there a function?
All they ask me for is to find the volume, so what do I put in there? 1.
Did we have something like that on the test?
I don't think so, not really like that. There was one dealing with polar coordinates, but
I remember working with R, which was
Oh, yeah,
two
yeah,
R's
definitely.
and then
Yeah.
two.
that last one, the
Yeah, I
that
know.
was switching to the polar, and you had the like the 1 less equal x squared
Yeah, it
plus
just goes.
So you would integrate with respect to Z before multiplying that R through?
And do you see how it doesn't really matter? If I multiply the R in, when I do it with respect to Z, R is a constant, so it doesn't really care. That's kind of convention to write it like that, but do you see how the R, I don't care if you put it there. It's not going to mess me up, because the first thing I do with respect to Z, R just kind of comes for the ride, right? R is a constant at first. So when you integrate here, 1,
You get 12 minus R squared minus R.
bless you. Yeah, because you'll get Z, and then evaluate it between these, so you get this.
All times R.
And now you get a nice little polynomial, bring that R through. Not too bad, right? You finish that out easy as that. And again, that's example 4, so if you want to see that finished out, go there. You should be able to finish it out nice. When you get here, you're like, oh yeah, thank God, man. It's just a freaking polynomial, please. So cylindrical, don't make more out of cylindrical than it is. You definitely want to try to graph your domain, your region that you're integrating over by itself, depending on the situation they give you. And then the Z should be pretty even. Either it goes up to Z equals 5, or it goes between Z equals this to Z equals that. That limit should be pretty easy to set up. Those limits on that interval for the DZ. Okay. Those of you doing physics, you're doing some cylindrical shapes.
Gaussian surface?
Yes.
It's not quite double integrals yet.
Not quite. Okay, yeah.
Can you move the whiteboard back?
Sorry.
Do you do those with double integrals? The Gaussian surface?
Can you do what?
Because we do it in 2D. Can you start doing it in 3D?
Yeah.
All I know is you still have 3 years of physics ahead of us.
So at some time in there, it's going to come in, right? Okay. So that was pretty quick. What we need to spend a bulk of our time today on is the next step, which is really kind of brand new. Not brand new, but new enough. And that's spherical coordinates. Actually, real quick, before I get too far away, let me put a little side note here. Some basic cylindrical equations. Like, oh, I keep hiding my notes from myself. Yeah. R equals A. Now let's just stop and think about what that might mean in cylindrical. If I just say that equation, R equals like 7. What would that set up? What's theta then?
Everything's
Everything, because if it's not in the equation, it's not contained. And z is everything, right? So if I just say r equals a, if I just say I just want you to go out r equals 7. So obviously I can pick up all this, right? And that's trying to be in the xy plane. It's not doing a very good job. But then also I pick up all the z's. So what do I end up with? This infinite cylinder. Cool. So r equals a is some kind of definition of a cylinder. If you do put restrictions on z, you can kind of cap it so that it's not some nifty infinite cylinder. So this is a cylinder. Let's see what else we're going to do. Oh, yeah. What about this? Theta equals some constant. If I just say theta is something,
Is it a plane?
I like it. It's going to be a plane. And to be honest, it's going to be like a half plane. So if you want to see, this is on page 925. Vertical half plane. Cool. So if you just tell somebody, I want you to face this way, you can go up and down as much as you want to. You can go out as much as you want to. Be careful. R says go out in the direction I'm facing. It doesn't say go back also. You with me? That's why it's a half plane. It's cut off at the origin.
So no negative radius?
Exactly. I like it. Let me see. Oh, and here's a nifty one. A cone. Now a cone, I want it to grow as I go up, right? So I want z to somehow be based on, if I move out a little bit more, my z should be bigger. Move out a little bit more, my z should be correspondingly bigger, proportionally bigger.
R equals east?
Yeah, so that's one example, but I can actually make it just any.
Constant R, right?
Yeah, I love it. So if I move out a little bit, my height has to go up. Move out a little more, it's got to go up a little more in a linear fashion, so I end up with the side of a cone. And then the fact that I haven't said anything about the angles, I get the entire cone. I move all the way around. How are we doing so far? Okay. So obviously, you've seen rectangular coordinate functions enough that I have to expect that you know what certain things look like. These are pretty brand new. I'm not going to expect you just to know very quickly. You could think about it for a minute, but I'm not going to expect you to know, okay, theta equals 7. What's it look like? So just realize how to approach thinking about these things, how to figure out what they look like. Okay. Spherical is going to be, just to warn you, it is even more counterintuitive than polar coordinates, when I had to introduce that r, and that wasn't that bad. That actually makes some sense. I've got to multiply theta by r to give it units. So in that respect, it actually makes some sense. The same thing happens in spherical, but it happens even more. Right? Because spherical, it has two angle coordinates. Okay? So spherical coordinates are rho, theta, and phi. Rho is really the three-dimensional analog of r. R I always think of as being just in the xy plane, just there. Rho is like the Greek letter r, so it's stepped up. Rho is r in 3 dimensions. How we do so far? Theta is the same old theta. So let me see if I can possibly, of course, maybe I should just throw the thing from the book. It's always a little less risky.
The other one's phi, right?
Okay, let me turn this sucker around. I like it. So here's the cool thing. Is that R would be this. So rho, I'm sorry, this whole thing. Rho is the, now it's in truly 3 dimensions, not just in 2. That's the connection there. Theta is the same old theta it always has been. It's in relation to the x-axis. Thank you, theta, for not changing. Phi is the angle down from the z-axis. So think about this. Before I even do any more of this, can you think about if I said phi equals pi over 3.
It'd be pi 3
So
from
60 degrees now.
So it'd be 60 degrees down. I didn't say anything about rho. I didn't say anything about theta. So what do I end up with? What image do I end up with?
Outside of the cone.
I end up with a cone, right? Because I just say, come down from the z-axis and now swirl all the way around and go out as far as you want. So it's this infinitely length cone that's got to be at 60 degrees from the z-axis. So what do you think are the limits on phi?
Pi.
Exactly. So phi can go from 0, get in there. It's a pi. So don't make 2 pi, right? 2 pi it would start to kind of come back on itself. Theta kind of picks up if I wanted to go down, but then I want to be back. Well, theta can swing me around. I don't have to go any further. I don't have to go down and then back up. No, the theta will swing me around there. Does that make sense?
Yes.
Okay, good, good, good. Let's see. That's the only new guy. These guys we're actually pretty comfortable with at this point. We know R, which is what rho really is, and we know theta. Okay. So I want you to realize, I think I've said this before, how many different coordinate systems are there? Yes, because you can make up now, many of them are modifications of known ones. So if you say how many families of coordinate systems are there, I personally know of about 20 something. And then you can modify each one based on your own specific needs, right? Because all you need is something that's consistent. Tell somebody to move, turn this way, move that way, go that way, right? Some of them are incredibly funky and they're only used for a specific type of function. If you just use those coordinates, integrals are easy as hell for that kind of function. You would never use it except for that specific kind of function. So obviously spherical should probably work really well. For example, spheres, yes. But anything that has that symmetry to it should work really well with spherical coordinate system. So how would integrals work with this thing? Well, that's going to take a little work here. And one of my favorite images is this hammer dude. I call him the hammer dude because boom, boom. So you got this in the book. Yeah.
Rho, what was rho again on that?
Rho is R, except now it's allowed to kind of point up. So in the past, R is only allowed to, turn and go that way, turn and go that way. Now I can say turn, and then angle from the Z and then go that way so far. And so now it can go in all 3 dimensions.
So R was just on the XY.
R is just in the XY plane. I like it.
So does that mean the arc length will always be maximum on the XY plane? Because as you go up, like there, it gets.
I see. Yeah, I get what you're thinking, and that will come into play when we talk about the integration. Okay, good. All right. Let me show you one image before we get into this that kind of talks about what was just said. Where are you?
Professor.
Yeah.
Why did you say this now establishes an infinite number of possibilities with there? You guys said you now have infinite.
No, not you can now. It's just true. And really, we got to be careful because there are an infinite number of functions, but you can classify them so they're not an infinite. There's a finite with an infinite number of tweaks you can make. Does that make sense? So there are officially an infinite number of coordinate systems, but you can group them and say, well, this is really just this one where the guy's turned this way instead of that way. You can classify them as certain types. So there's not an infinite. There's a finite number of them that you can play with each one in infinite little ways. Does that sort of make sense? Of course, in this class, we're not going to start talking about 20 coordinate systems. Don't worry. Yeah.
Wouldn't pi be enough to go from 0 to pi out only because we can cover that area by theta?
That's the point. Yeah. So I had up here 0 to pi for phi, for phi.
I was saying pi out.
No, you actually do have to allow it to go to pi, because what if you want a cone? Shoot, I've already lost. What if you want a cone that's in the bottom hemisphere, right, below the XY plane? Your phi has to go down all the way down there. You see what I'm saying? And then you can get that cone there as you twirl it around. So if you only let phi go from 0 to pi over 2, you never get down here. Nothing will let you get down there. That's what lets you get down there, and then theta is what gives you on the other side. That's why it doesn't have to go past pi. It doesn't have to go back there, because you just rotate the bad boy, right? Cool. The point I want to make here is what's that?
That is.
R. That's R. So R does officially live here. Z just kind of picks the whole thing up out of the XY plane, right? You with me? Rho would be this. Rho is allowed to actually point out of the XY plane, whatever direction it wants to. That's the difference between rho and R. Same stupid thing. They both tell you how far to go once you turn the right way. It's just how rho can tell you how far to go in all these different directions. Yeah?
Rho is always going to go to a vertice.
To what now?
To like an edge, a corner, vertice of your shape.
Well, remember, rho is going to point to whatever the point is. So if I want to get to that point, I could tell somebody, okay, I want you to come down this far, rotate this much, come down this far, and now go, let me see if I can get this, go that far, right? So rotate this much, come down from Z that far, and then go that far to that point. That's the idea. So rotate, look, and then go. Does that make sense? Sort of. So I always think about, the guns and things. I mean, you can turn the gun all the way around, and you can move it up and you can move it down. There's no reason to be able to go that way. What the hell would you want to do that? He's behind you now. Shit, no, just turn the damn thing, right? So that's the idea of theta being 0 to 2 pi, but phi being only 0 to pi. You don't want to kind of come back on yourself, right? That'd be kind of silly. So I'm not military minded normally, but that gun idea makes total sense. You can move it up, shoot, and how far your bullet goes, that's rho. The direction you turn is theta, and how much you push it up or down, that's phi. Does that make sense? Okay, all right. So coming back to this, coming back to the hammer. This is going to take a little explanation. And as always, I desperately want you to get the derivation, but if you don't, you still have to kind of know how to set up the integration. All right, so it's going to be a little more involved than r dr d theta, or dz r dr d theta. Because now I have two angle elements, right? So each one of those should require what to make me have true units at the end?
2r.
Well, in this case, 2 rows, right? 2 little p dudes. You with me? A little bit. Okay, a little bit. Some of you guys?
Rho squared.
So at the end, you're going to have rho squared somehow. Exactly. Because theta is going to need a rho to get its arc length. Phi is going to need a rho to get its arc length somehow. So in the end, you're going to have rho squared. So let me remind you about a couple things before we get into this integration. That's, I always hesitate to bring this up, but that submarine problem, I think that should be all I have to say. Do you guys remember that?
Yeah.
That actually got you ready for this, or it was the attempt to get you ready for this. If I have point out here in space, and I want to kind of break this up into pieces, and all I tell you is this, I tell you this angle here, and I tell you this angle here. If you remember, I told you both of those. I told you it was headed southwest, that was the theta, and it was going down or up, and that would be the phi. You with me? Mm-hmm. So the first thing I can do with this is to break off the z component. To break off this component here. So let's call this, let's just go ahead and call this rho. That's what that length is, you with me? Yeah. Because that's what it would be. What will this component here be?
Z
cosine theta.
Phi measures how much it's kind of come down from the phi is that angle. I want to know what that length there is. Yeah, this will be rho cosine phi. Right? I've got my little right triangle here. This is the base, that's rho cosine. Or if you like SOHCAHTOA, whatever the hell. So I told you before, you probably want to let go of that. Doesn't really help you out too much. That's the x piece. If I look at it like that, that's the base. That's the cosine. Then what's this little dotted line here?
That's rho
sine phi.
Rho sine phi. Now I still haven't. Now I got what z is, don't I? So I'm kind of working out what the conversions are here before I throw us into the full. How do we integrate things? How do we figure out what that dv is going to be for my triple integral? So z is rho cosine phi. I don't have a freaking clue yet what x and y are. So right here, what would the x piece of this be?
Rho sine phi times rho.
Be careful now. You mean so now I've got rho sine phi, and I want you to notice something. This might help us out a little bit, and this will help us out a lot actually. Rho sine phi, since I've pushed it into the xy plane, and considering the earlier conversation we had, what does rho sine phi act like now? Since it's in the xy plane. Acts like r. So call this r. So what is x in polar? R cosine theta. So then here it's rho sine phi cosine theta. Pick a theta.
It would actually be 180 minus theta.
Don't worry, the fact that it's back there, the fact that theta is bigger than 90. I mean, I could have put us in the positive one to not worry about negatives, but you with me?
Okay.
Yeah. So that still holds, right? It's theta is bigger than 90, therefore cosine is going to be negative, so it's fine. So that x will be negative. What about the y piece, of course?
Rho sine phi.
Yeah, this will be r times sine theta. Now, if you remember the submarine problem, the mistake people made was they didn't realize they took a couple of trig things in a row, and that's exactly why, because one of them has to be broken up again according to the other angle. But a really nice way to look at that is, like I said, this piece is really just r. So you pick up your old polar transformations. Okay. Now, the other way is kind of funny. What do you think rho squared is going to be? In fact, let me do it like this. What's x squared plus y squared?
R squared. R squared.
Yeah, be more specific. Yeah.
E squared.
Right, once you get this squared, cosine squared, this squared, sine squared, when you add them, that becomes 1, so you end up with rho squared sine phi squared. How are we doing so far? Is that all right? It would be r squared, but what's r now for us in spherical? Rho sine phi. Okay, so far so good. So then what's x squared plus y squared plus z squared? It'd be rho squared sine squared phi. You put that square where it should be. Plus rho squared cosine squared phi, which of course is just
rho squared.
rho squared. Thank God, because r squared is x squared plus y squared. I hope to God that rho squared is just freaking x squared plus y squared plus z squared. And it is. I mean, you remember the distance formula between points in 3 dimensions is the same idea. That's really what that's related to. Because rho is the length of that. The distance from the origin to the point. That's what it should be. Okay, how are we doing so far? Nothing major yet, really. Just these little playing around with conversions. So you know you're going to have some problems that deal with converting things over. So what about integration? So here's where the hammer comes in. So I like what they've done here, and can you guys kind of see what's going on here? I've got a little element of volume. They've actually made it really big. That's kind of nice. This element of volume that I've got. And they based it on this average rho, average phi, average theta, just because you can pick whatever point you want to. That's the easiest point to pick. So that sounds very similar to what we did with polar intervals, right? Does that sound familiar? Yeah. So we had to define like a rectangular, a polar rectangle and so forth. So we're doing a similar thing. We got the polar rectangle. That's the same as always. It's just our good old polar rectangle. A couple things happen though. So now I've got to figure out the sides of that box. If I know the sides of this stupid box, I can just put them together at the end of the interval and I'm ready. Officially, I left the summations, but we know that that will become the interval after I take limits. How are we doing so far? Okay. So I'm glossing over a lot of work, but it's all the work we've done before already. So why do it again? So this side here is the easiest. So this is rho and this is rho in two different ways, right? This is rho for the lower part of the box, and that's rho for the upper. So that side is just going to be delta rho. Is that cool? Let me see if I can hazard an attempt at this box. It's going to be funny. All right. It's not too bad so far, Jeff. You haven't done much yet, Jeff. Okay. Yeah, that's basically it. Cool. That's enough for there. That's all we need. Okay. Let me just deal with my weird ass loaf of bread up here on the board. So this piece here is just delta rho. Is that cool? That's just how much the difference in the rows, and we're of course going to let those go down to 0 in the limiting process that we're not going to do. The green line is easy enough. I've got to get that. It's related to phi. Because this is phi at one point, this is phi at the other side. So that's delta phi is officially the angle between those two. To make it an arc length, I got to multiply it by the rho. That piece is not too bad either. So this arc length here is rho delta phi. I'm just dropping off the k's, just to get to the point. So the last side, we got one side left, and I must have left it last for a reason, and I did, because it's the hardest one to figure out. But let me see if I can make this not too bad. You guys see this rectangle? That's a good start, Jeff. You guys see this triangle?
Yes.
All right. And this little piece here, this little piece there, is an arc length on a circle that has this orange line as a radius. So I want you to realize here, that's this. But if I lift this up, doesn't that move in?
Yes.
Like the shadow of that doesn't move in? So this radius is not the same as rho. It's going to be some trig function, some percentage of rho. So as I lift that up, that's not going to be nearly as big. That's what it looks like now that I've lifted the hammer up that far. How are we doing so far? So I can't do rho times delta theta because it's not just rho. It's now some piece of rho. So this triangle, and of course there's the answer there eventually, but here's the triangle. Here's delta phi. Let me see where I want to go. Here's delta phi. But this triangle, and this is rho, what's this piece going to be? Or I already identified this piece earlier. That's rho cosine. That's the z, right? Rho cosine. So of course this piece has to be rho sine. So the tricky part, now that wasn't the tricky part. The tricky part is to realize that's the radius of the circle that piece sits on, this little arc length. That little arc length has radius this. So to get the actual arc length, I've got to take the radius times delta theta to get that angle, right? It's r theta. So there's the r times delta theta to get that arc length. So this back root here, which I think I can do. Yes. All right, screw it. I'm not going any further, Jeff. I've lost it. Oh, here it is. All right, that back side there is going to be rho sine phi delta theta. So this is like my r up there for that circle that arc length is coming from, times the angle will of course be the arc length. So now I've got length of this, length of this, length of that in the back. This is kind of like the height of my bread. And this is the length and the width of my bread. So don't I just multiply all that stuff together? So then I get, let's just kind of multiply it. Just throw it all together at first. And then we'll put it in the right order. So there it all is, right? There's this piece here, and of course that piece is the nicest piece up there. There you go. So the order that we normally do this in, and again, this sort of doesn't matter to a point. Oh, I forgot which way. All right. Yeah. I think I did it differently before. Yes, sir.
Which one is delta rho?
That's that's this piece here.
The red?
Yeah. Because the bottom of the box only goes out to like row 1, but the top is row 2. It's a little further, isn't it? So what's the length there? The difference in those two, delta rho. Cool. Okay. And that's why, of course, this is delta phi on that side times the radius there to give the actual arc length. Okay. How are we doing so far? So the integral for spherical would look like this. Integral function of r theta phi rho squared sine phi delta rho delta phi delta theta.
To be rho theta phi, not r.
R, yeah, or thank you. Gruesome. So as you might imagine, if we did a lot of these integrals, you would probably at some point hit some interesting methods you must use because of that extra sign phi sitting in there. And your functions that you're integrating over could themselves have trig functions in them of phi or theta. So you could end up with a situation where you have like a sine squared, cosine cubed. So you got to remember how to attack those. Right. Let's do let me see if I have an example.
Is that phi theta? Or phi, or rho? That's rho theta phi?
Rho theta phi.
So, we don't need, oh.
Well, they have rho, yeah, or rho phi theta. How did I write it? Yeah. I've seen it both ways. I think we did.
So it doesn't matter on the order, you just have to
Yeah.
keep the limits the same?
Yeah. This order, I mean, what do you think? They do talk a little bit about, you know, what order to choose, because you can start to change things around, but it kind of makes sense for theta to be the last one because it's almost always going to be either a full rotation or a partial rotation. So those are going to definitely be constants normally. Phi should also be either constants or possibly between two functions, but normally it's going to be constants. The one that could possibly be normally a function would be rho itself. They might say rho goes between 4 cosine theta sine theta, something else. That could be the one. That's why it makes sense to put that on the inner one first. That would be the one that you do first. Let's do one out of the homework. Number 31. That's actually, this is, well, that's fine. We'll do this one first. Now, which, you can do this on purpose, by the way, but we'll kind of do in the order that we did today. Which system should I use to do this? Spherical or cylindrical? Because they give it to me in terms of z, right? So, and what's the very first thing I notice about this equation here that can help me?
You can turn it into arc, right?
Exactly. So it actually goes from z equal to root 29 to z equals to root 4 plus r squared. Now again, how do I start to figure out what my limits are gonna be on my integral for R, for example. Set them equal to each other, so first thing I do is square it, so I get this. So I end up with R is 5, cool. Put R out to negative 2. So R has to go from 0 to 5. So for cylindrical, it's going to be, and this is asking for the volume of the gift. It's going to be dz r dr d theta. Z is easy enough. Which one do you think goes on the top? Which one goes at the bottom?
The top will be square root of 4 of this.
5 goes on the top. 5 is the ceiling.
Well, now for R, it'll be 0 to 5. For Z,
Be square root of 4 plus
yeah, that'll be what, where? Be careful now.
Root 29 is on top.
Yes, cool, right? Because if R is 0, Z is 2. And if R is the biggest, if R is 5, Z is root 29. So that's the largest value of Z. So that's the, this is what would this look like by itself? Z equals root 29.
Oh, just the line.
Just a plate, right? So, and this would look like what?
A bowl.
Yeah, some kind of a bowl, right? So then what this is doing, that's like the capping the bowl. I'm saying the bowl goes as far, put a little cap on top of that bowl, so it stops right there. We figured out that if I go up to R equals 5, I get out to where these two meet. So here it's going to be root 4 plus R squared. It's root 29.
And from 0 to 2 pi.
And of course for theta, almost always, but be really careful, almost always it'll be 0 to 2 pi. Here I want to get the whole bowl. They didn't say to do half of it or something. So 0 to 2 pi. So take a minute and try to do this integration. There's a little bit of, it's not too bad, there's a U sub in there somewhere. And I'll pick out one for spherical. There you go. Bless you. Bless you. Bless you. Yeah.
And there, the Z is the Z is representing the in respect to rho that's in there, or
Well, this is, we decided to do cylindrical here because they give it to me in terms of Z and something I can make into R. You see what I'm saying?
okay. Also, you just
So if they give you functions in terms of Z, I'm probably going to try to attack it with either rectangular or change to cylindrical. Yeah.
okay.
And the nice thing with this homework, and I'm going to do something similar on the test, they do it by sections. They say integrate these using cylindrical, and integrate these using spherical, so you don't have to sit down and think which one's the best way to go. That would be the next level after learning how to do this, is learning how to identify when to do which one. Given some general.
So there are times where we cannot use cylindrical, because cylindrical is
There's not times you
way
can't.
easier than spherical. Spherical is so complicated with the signs because the
True.
Symbols we are not.
But you
used
do
to.
have certain intervals that would either be difficult to the point of being, crazy, or even possibly impossible, depending on what the integrand is. So you can make it easier because you have spherical symmetry in the problem, or it could be something that spherical can do that you can't do in some other integration. And we've seen that before. We've seen something simple as if you just switch the limits of integration, it goes from impossible It's easy. So changing entire coordinate systems, that shouldn't confuse us that one might be impossible and I switch the entire coordinate system, now it's easy. That's what we're talking
I
about
mean,
now.
this is not much different from what we had in, I think, 13.3 is the same concept for R and theta, it's just we added.
And at that point, I think I said something about cylindrical at that point, that we were basically doing cylindrical coordinate system, because all we were doing was throwing a Z in with the R theta.
Yeah. So it's just the Z which is different,
Exactly.
the rest is just the same.
Exactly. So don't make too much of this stuff here. So when you do this first step, get there. Now, for some reason, people get confused. This piece will be easy enough, right?
Then you get a use of.
This piece will require a U sub, so you split these up a little bit, at least inside here. I wouldn't write two whole intervals necessarily. This piece will be
R squared.
1/2 R squared, radical 29.
root 29 over 2 R squared. Now this piece, you'll need a U sub.
1/2 R.
Yes, you'll have over 2. Is that cool? You guys with me?
Yeah.
A little bit? So then you basically get, I'm trying to do, alright, I understand. So you'll get like U to the 1/2 over 2. There's your du. So I still got a little bit of work to do here.
1/3.
So I still have my limits to do too.
35.
So I get root 29 over 2 R squared minus U to the,
3/2.
with a 1/3 out from right, it'd be a 2/3, 2's cancel, I get 1/3 U, and U was 4 plus R squared.
Shoot, I forgot what that's. 5.
Okay, you stop right there for a second. So don't, for some reason, every now and again, I'll see people have trouble when there's part of it that needs a U sub and part of it that doesn't. Just do the part that doesn't directly, and for some reason people think they have to add something in it. No, it's just that piece that needs something added. Right, so I have to throw a 1/2 out in front of the whole thing. That doesn't need an extra 1/2. That guy does, right? So I can take care of that, bam, more directly. And now you just got to throw in the 5 and the 0. Let's see. So if we do that, 5 here would be, yeah, 25
Root 29 over 2.
minus,
1/3.
good, 5,
29.
yeah,
29. 3/2.
or just that there. Over, did I lose my over 2 or just, no, that's right, we sucked it in, that's right.
Minus 1/8
Good. And then when you throw a 0 in, almost good. Throw a 0 in, square root of 4 is 2 cubed is 8/3, minus a negative. Okay. That right there, real quick, that right there is the 3/2 power. 3/2 power just means a full plus a half. So a full 29 plus a half of 29. All right, so go ahead and break it up, because now I have kind of like terms here, right? They're both root 29s. I could put those together.
Oh,
And this integration right there is beautiful. Very often this happens. All that's going to do to me is do what?
Multiply the whole darn thing by
Yeah, the whole
2
thing's
pi.
going to pick up a 2 pi. I'm going to integrate this to get a theta, 2 pi. So 2 pi times, if I triple this, I get 75. Double this, I get 58. 75 minus 58 is 17. Plus, let's go ahead and do this. Plus 16/6 is equal. And then kill that. There you go. You get that beautiful thing. Gruesome. And again, the integral was decently easy to set up, because all I had to do was figure out where these guys meet. That happens a lot. Figure out where they meet by doing this here. That tells me R theta almost always goes 0 to 2 pi, but not always. And Z was easy. Z, they gave me directly what it does. So cylindrical is not crazy, guys.
Where did the 8/3 come from here?
Oh, sorry, when you plug in a 0 here,
Oh. Yeah,
you get 4, square root of 4 is 2, 2 cubed, yeah. So be real careful, because I did this a lot when I was a student too. I'd see a 0 and think, oh cool, I don't have to worry about it, when actually, shit, it's actually adding something. So don't neglect the poor little 0 limit. So let's try a spherical one out. And then I think I'll call it a day. I want to do one like number 41, where they give us a description of the region instead of directly like that did. Turn this dude off. Winner. 41. Let's say and they tell me D is the region between spheres of radius 1 and 2. Yeah.
So that just means there are limits for rho are 1 and 2.
I love it. So right off the bat, you know that your limits for rho. So rho, another way to look at rho is it's just a radius for a sphere, so that's why it's got to be allowed to move in all 3 dimensions. Whereas r is a radius for a circle, it can only move in the 2 dimensions. Is that cool? So right off the bat, I know that rho goes from 1 to 2. Sweet. And the nice thing about spheres is they go the whole gambit. Unless they say the upper sphere, or they tell me the sphere in the 3rd octant or something weird. Yeah.
Isn't simply x squared plus y squared plus z squared?
Definitely. So this is can you imagine trying to do this integral in rectangular coordinates?
No.
Oh my God. I mean, no U sub's gonna say your ass here, right? So you'd have to do, so it would basically be, if you want to do dx first, y and z are constants, x squared plus constant squared. It sounds like it might be a
Mess.
mess, is one way to describe it, but what would you do if you had something like that?
It'd be a right triangle trick, right?
Could be a trig sub, right? Can you imagine that? I don't want to imagine that, so let's not. So that's one that's screaming to be done in spherical. So rectangular would so suck. Well, that sounds like a good idea for a bonus question. But bonus, who gets the bonus? So how do I rewrite this? And then we'll worry about the limits. Like you said, this should be 1 over. Be careful. 1 over rho.
3 halves.
What is rho?
Rho.
Rho squared is x squared plus y squared plus z squared.
So rho over 17.
So if you wanted to, you could say this is rho squared to the 3 halves, but I would hope you could just go directly to this is rho cubed. Right? You guys see that? That's rho cubed because this to the 1 half is rho cubed. Okay, cool. And then what is my
Rho squared sine phi.
so rho squared sine phi d rho
D phi.
d phi
D theta.
d theta.
You
Cool.
can cancel out your rho.
Yeah, I love it. So the first thing that happens is a couple rows go away. It's kind of nice. And what are my limits going to be though? So the limits on rho are easy, and limits on phi
would be
0 to
0 pi.
0 to pi because I want to catch the upper hemisphere and of course the lower hemisphere. So if they said the upper hemisphere, between the upper hemispheres of radius 1 and 2, you would go, phi would go from 0 to pi over 2. That's the kind of thing you got to think about. So a sphere will capture the whole thing. So you let everybody run as much as they need to, and then rho will tell you how big your spheres are. So your angle variables will run the whole gamut. 0 to 2 pi for theta, 0 to pi for